Можно? Okay, so our main goal for today is to introduce the functor K0 for unital rings. Well, first of all, why do we care about rings? Well, of course, our main objects are still sister algebras. Some time ago, I've already told you that there are actually two different versions of K-theory, namely algebraic K-theory, which deals with arbitrary rings, and operator K-theory, or maybe more exactly, functional analytic K-theory, which deals with sister algebras and more generally with Banach algebras and topological algebras. So both versions of K-theory have common roots in algebraic geometry and in topological K-theory, but they are quite different from each other, in spite of the fact that there are many interesting relations between them, but nevertheless they have rather different flavors. But nevertheless, there is an important common point at the foundations of these two subjects. And this is the definition of K0. So in summary, K0 for unital rings is the same as K0 for unital sister algebras. And because of this, we'll first define K0 in the context of unital rings. We will study some algebraic properties of K0. And only then we specialize to sister algebras, and we'll study some properties of K0 which are specific for the sister case. Okay, so suppose that R is a unital ring. That is a ring with identity. We will deal with left modules over R. And the category of all left R modules will be denoted like this. This is the category of left R modules. And since R is assumed to be unital, we will adopt the standard convention that the identity of this ring acts as the identity transformation on modules. We have the following identity for every module. So let's now recall the following pure algebraic definition, which is at the same time a theorem. We say that a left R module P is projective if and here we have at least three equivalent definitions. If it satisfies any and hence all of the following equivalent conditions. So the theorem is that the conditions are indeed equivalent. The first definition is given in terms of so-called lifting property, which can be visualized as follows. So for every surjective morphism of modules, as denoted by sigma, from M on to N, and for every morphism phi, from P to N, there is a lifting, that is, there is a morphism psi, from P to M, psi, such that the diagram commutes. Of course, psi is not necessarily unique. There can be many such morphisms. If there is at least one of them, then we can add any other morphism whose range sits in the kernel of sigma. So in general, there are many liftings of this form. This is the lifting property of P. Condition 2, which looks weaker, but in fact it is equivalent to 1. Every surjective morphism, sigma from P onto M, is actually a retraction which means that it has a right inverse map, a section. There is a morphism psi from P to M such that if we first apply psi and then sigma, then we get the identity map of P. And condition 3, which is also quite useful, the home functor, where P sits in the first argument. So this functor acts from R modules to abelian groups. This functor is exact in the sense that it takes short exact sequences of R modules to exact sequences of abelian groups. By the way, I can put brackets here because if it takes preserves the exactness of short exact sequences, then actually it preserves exactness of arbitrary sequences of R modules. If you have never seen this result, I recommend you to prove it as an exercise. This is quite standard. I'll give you just a couple of hints. First of all, clearly choose a special case of 1, but 1 can be also easily deduced from 2 as follows. If we have a diagram of this form, it's useful to consider the so-called push-out of this diagram. So this is the following module, M cross P over N, and it consists of all pairs MP in the product of M by N, such that sigma of M equals phi of P. And there is an obvious projection of this module onto P. So if we have property 2, then this map is a retraction, and from this we can easily find psi satisfying this property. So this trick shows that 2 implies 1. And to prove that 1 and 3 are equivalent, just observe that property 1, means precisely that this functor, the home functor, takes surjective morphisms to surjective morphisms. It preserves surjections. And by using the fact that this functor is always left exact, we see that it is actually, if property 1 is satisfied, then this functor is actually exact. So an important special case of a projective module is a free module. So we have the following definition. We say that a left R module F is free if it has a basis that is a subset that's denoted by B, such that every element in F can be uniquely written in the following form. As a following finite linear combination Ri, Bi, where the elements R1 to Rn are in the ring, and B1, Bn are in this subset B. Free modules can be also equivalently characterized as follows. Here's a simple exercise. F is free if and only if there is a set that's denoted by I, such that F is isomorphic to the following module. Let's denote it like this. So this is simply a direct sum of many copies of R. So here, every Ri is equal to R. In particular, it is free and finitely generated, and we are mostly interested in finitely generated modules. F is free and finitely generated, if and only if it is isomorphic to R to the power n for some non-negative integer n. In fact, part 2 is not immediate from part 1. So what is essential here? More exactly, I claim that if F is finitely generated and has a basis, let's denote this basis by B, then B is necessarily finite. B is finite. This is maybe not entirely immediate, but this is simple and useful exercise. Okay, so now let's observe that every free module is projective. Let it be proposition 1. If F is free, then it is projective. And the proof is very easy. Actually, we can use any of the equivalent definitions of a projective module. Well, for example, let's look at property 3. If we apply this functor to a free module, which is of the form given in this exercise, then what we get is naturally isomorphic to Mi, which is defined in the same way. This is just the direct sum of many copies of the same module M. And this is a natural isomorphism. So if we now look at this functor, it takes every M to Mi, and this functor is obviously exact. So this module is projective. Alternatively, we can look at this diagram, and by using the surjectivity of sigma, first lift phi on the basis, which is always possible, and then simply extend the resulting map psi, which is defined on B, by linearity to the whole of F by using the uniqueness of this decomposition. So anyway, we see that every free module is projective. In the general case, the converse is not true, and here's a simple example and exercise at the same time. Let's take any field, K be a field, and let R denote the matrix algebra, Mn of K. So it acts. No, this is not the product. This is the same construction as here. Yeah, of course. If you're right, yeah, because this is a coproduct here. Just, thank you, that's correct. This is the product of many copies of M. So here we have direct sum, then here and here, of course, we have a product. So to give a map from here to here, we simply take every element of the basis to an arbitrary element of M. And so as a result, we get a family of arbitrary elements in M, not necessarily finite. So this is indeed a product. But this functor is, nevertheless, it is exact. So our module is projective. If we now come back to this example, we take the matrices, and by n square matrices over K. This ring acts on K to the power n on the left, so just by matrix multiplication. So Kn becomes a left module over this ring. And the exercise is to show that it is projective, but it is not free unless n equals 1. In fact, it turns out that, but this is essentially this is a bit harder to show that all modules over this ring are projective. But not all of them are free. So the class of projective modules is bigger in general than the class of free modules, but on the other hand, projective modules can easily be characterized in terms of free modules. Before giving this characterization, let me make a short remark. This will be proposition 2. A short remark about direct summands. If we have two R modules, M and N, then I claim that N is isomorphic to a direct summand of M, if and only if there is a retraction, as noted by P, of M onto M. That is a morphism which has a right inverse. Well, this is very easy. Indeed, if it is isomorphic to a direct summand of M, then we can just replace M by its isomorphic copy, and we may assume that M is just the direct sum of two modules, and prime. And it's very easy to construct a retraction. This is just the projection onto the first direct summand. And conversely, if we have a retraction of M onto N, so this means that there is a morphism I, which acts in the opposite direction, and which is a right inverse to P. Pi is the identity map of N. Then we consider the following endomorphism, E, which is just IP. So it acts from M to itself. And it is idempotent. Clearly, E squared equals E. And because of this this identity. And it's a very simple exercise that for every idempotent endomorphism of any module, we have the following direct sum decomposition. The image of E plus the image of 1 minus E. This is true for any idempotent endomorphism of any module. So if we now look at the first summand, the image of E, first of all, we observe that this is equal to the image of I, because the P is surjective. So this equation readily implies that P is surjective. So the image of E equals the image of I. But on the other hand, the image of I is isomorphic to N because I is injective, again by this formula. So we see that N is isomorphic to a direct summand of N. Let's now observe that the projectivity is inherited by direct summands. This is proposition 3. If a module P is decomposed into two direct summands, say P prime and P double prime, then P is projective if and only if both P prime and P double prime are projective. Well, this is actually a simple observation, because if we look at the respective home functor, from P to M, this is naturally isomorphic to the direct sum of from P prime to M and from P double prime to M. And this isomorphism is again natural, so it extends from modules to exact sequences, so we may assume here that M is not just a module but is a certain diagram of modules. To complete the proof, it's enough to observe that the direct sum of two exact sequences is exact. The direct sum of two exact sequences is exact. And so if both P prime and P double prime are projective, then for every exact sequence of M of left R modules, this sequence is exact and this one is exact. So this one also is also exact, and hence P is projective. And on the other hand, a direct summand of an exact sequence is also easily seen to be exact. So if P is projective, then for every exact sequence M, this sequence is exact, and therefore both this one and this one are exact. And so both P prime and P double prime are projective. Okay, now we can easily characterize projective modules in terms of free modules. This is our proposition 3. And our module P is projective even only if it is isomorphic to direct summand of a free module. And since we are mostly interested in the finitely generated case, and our module P of a free finitely generated modules. Free finitely generated R module. It is of the module Rn for a suitable positive integer n. Well, I'll prove only part 2. We are mostly interested in the finitely generated case. The proof of 1 is almost identical. Well, if we know that it is isomorphic to a direct summand of a free module, of a free finitely generated module, then it is projective by proposition 3, and that's it. So this readily follows from proposition 3 and from proposition 1. So a free module is projective, and the direct summand of a projective module is projective. And clearly, a direct summand of a finitely generated module is finitely generated. And conversely, if we assume that P is finitely generated and projective, so since it is finitely generated, it follows that we have a surjection sigma of Rn for a suitable n onto P. This is equivalent to the fact that it is finitely generated. But since it is projective, we deduce that sigma is a retraction. And now it remains to apply proposition 2. So P becomes the direct summand of Rn. Okay, so we are interested in finitely generated projective R modules. Let's introduce some notation. First of all, the category of finitely generated projective R modules will be denoted like this. This is a full category in the category of all left R modules. Subcategory of finitely generated projective modules. And we will be interested in these modules up to an isomorphism. So more exactly, we will introduce the following set, which will be denoted by V of R. This is the set of isomorphism classes of finitely generated projective R modules. So for every finitely generated projective R module P, the respective isomorphism class of P will be denoted like this. This is an element of V of R. Well, first of all, why is it a set? There is a delicate point here, because the class of objects of an arbitrary category is not a set, but V of R is a set. Remark. V of R is indeed a set because every finitely generated projective R module P is isomorphic to the image of a suitable idempotent E, like in the proof of proposition 2, which acts on a free finitely generated module. So it is isomorphic to the image of E for some idempotent E acting on a free finitely generated module. Clearly, the set of all such idempotents is indeed a set. So V of R is also a set. In fact, this is not just a set. This is an abelian semigroup in a natural way. It's a simple exercise to show that V of R is an abelian semigroup with respect to the following operation. You have two elements of this semigroup, which are represented by modules P and Q. Then we can define their sum to be the isomorphism class of the direct sum of P and Q. So we already know that the direct sum of two projective modules is projective. And so this is a well-defined operation, which makes V of R into an abelian semigroup. Well, let's look at some simple examples. If you take any field, K is a field, then we know from elementary linear algebra that finitely generated k-modules are just finite dimensional vector spaces. Over K. And of course, all of them are free. Every finite dimensional vector space has a basis. All of them are free. In particular, all of them are projective. And of course, another standard result of linear algebra is that Km and Kn are isomorphic, if and only if the dimensions are the same, if and only if m equals n. So as a result, we see that the semigroup V of K is nothing but the additive semigroup of non-negative integers. In fact, and this is a standard exercise, the same is true if our ring is the ring of integers. Because a finitely generated abelian group is projective, even only if it is free. This can be deduced from the structure theorem for finitely generated abelian groups. And also, it's a standard fact that two such free abelian groups are isomorphic if and only if m equals n. So we have the same situation as in the case of a field. And the fact this can also be generalized to any principal ideal domain. The same is true for any principal ideal domain R. A finitely generated R module is projective if and only if it is free, and the two such modules are isomorphic if and only if they have the same rank. Okay, let's now observe that V of R is actually a functor. It is natural in R. And this follows from the next proposition. If we have a ring homomorphism, F from R to S, a unital ring homomorphism, and P is a finitely generated projective R module, then if we apply the following functor, so-called extension of scalars, to P, then the resulting S module is also finitely generated and projective. It's finitely generated and projective. The proof is very easy. First of all, we observe that this is true if P is free. And if P is not free but is finitely generated and projective, then it is a direct summand of this module. And this functor is additive. It takes direct sums to direct sums. So if P is isomorphic to a direct summand of another module Q, then S tensor P is isomorphic to S tensor Q. And that's it. So if P is projective, then it is a direct summand of a free module. And so this one is a direct summand of a free S module. By the way, another proof, which is also quite short, we simply look at the respective home functor and observe that it is isomorphic to the following one. Restricted to S modules. This one is exact on R modules, and moreover it is exact on S modules, and so this one is also exact. So as a corollary, we deduce that if F is a unital ring homomorphism from R to S, then F induces a semigroup homomorphism V of F, which acts from V of R to V of S by the following simple formula. It takes the isomorphism class of a module P to the isomorphism class of S tensor P. And this is easily seen to be semigroup homomorphism. So as a result, we have a functor from unital rings to a billion semigroups. Unital rings to a billion semigroups. This is a functor. This functor has the useful property of being additive in a suitable sense. Well, if we take two unital rings R and S, and take their direct sum, then the respective semigroup is naturally isomorphic to V of R plus V of S. Because every finitely generated projective module over this direct sum ring is naturally decomposed into two summons over R and over S respectively. Well, some people prefer working with right modules instead of left modules. Well, in general, our modules, if R is not commutative, then our right modules and left modules are not the same. And in general, there is no equivalence between the category of right and left modules. But if we restrict to finitely generated projective modules, then we have a full symmetry between left and right. So more exactly, we have the following simple result exercise. Let's look at the following functor. So more exactly, if we take left R module R, left R module M, then the group of homomorphisms from M to R has a natural structure of a right R module. With respect to the following operation, if F is a homomorphism from M to R, and little r is an element in R, then the homomorphism Fr takes M to F of Rm. So in a sense, this module is dual to M. If R, in a special case where R is a field, this is just the dual vector space. In the general case, this operation is not a bijection, is not an equivalence between the respective categories. But if we restrict it to finitely generated projective modules, then it becomes an equivalence between finitely generated projective left R modules and finitely generated projective right R modules. This functor is, of course, is contravariant, so to get an equivalence, we must replace one of the categories by the opposite one. And this is an equivalence. And this easily implies that we have a natural isomorphism between V of R and V over the opposite ring R up. Because the right, because the left modules over this ring are the same as right modules over R. Well, in the general case, this semigroup V of R can be quite complicated, even for nice rings R. So it turns out to be convenient to replace, to make V of R into a group, which is much more manageable and useful than V of R itself. Or more exactly, we are going to replace V of R by a group in a natural way. By a group which remembers a lot of information about V of R. Now, some information is lost, but some important information about V of R survives. In fact, the respective construction makes sense for any abelian semigroup, and it is called the group completion or the Grothendieck group. So let's give the respective definition. Suppose that we have an abelian semigroup S. An abelian semigroup. Then the Grothendieck group or the group completion of S is a pair consisting of an abelian group GR of S. This is an abelian group. And I is a semigroup homomorphism from S to GR of S. Semigroup homomorphism, which has the following universal property. Let's draw a picture. This is S, this is GR of S, and this is I. So the universal property is that for any abelian group H, abelian group H, and for every semigroup homomorphism F from S to H, F, there is a unique group homomorphism F hat, which makes the diagram commute. Such that the diagram commutes. So this is usual universal property. We can equivalently write it in the form of the following bijection. There is a one-to-one correspondence between the set of all abelian group homomorphisms from GR of S to H, and the set of all abelian semigroup homomorphisms from S to H for every group H, for every abelian group H. Well, it's immediate from this definition that if such an object exists, then it is unique in the obvious sense. So the uniqueness here means that if we have two such Grothendieck groups, say gr of S and gr prime of S, and I prime are the respective homomorphisms from here, from S to these two groups, then there is a unique group isomorphism between them, which makes the diagram commute. It is unique. So this is the general uniqueness property of an object which is defined in terms of such a universal property. How about the existence? Well, we will see shortly that this group always exists. But first of all, let's look at some simple examples. Of course, if S is already a group, then gr of S is just S, and I is the identity map. This is immediate from the definition. So a trivial example, if S is empty, then the Grothendieck group is 0, because, well, there is only one map from an empty set to H, and the only one group homomorphism from the 0 group to H. If we apply this construction to non-negative integers, or if we like, we can take all positive integers, the result will be the same. This is the group of integers. For the simple reason that a semi-group homomorphism from positive or from non-negative integers to H is determined by a single element in H, and this element can be arbitrary. So to give a semi-group homomorphism from this semigroup to H is the same as is equivalent to choosing a single element in H, and this gives us this isomorphism. If we take the semigroup of all non-zero integers, the multiplicative semigroup of all non-zero integers, then what we get is the semigroup of all non-zero rational numbers. This is an exercise for you. Finally, let's come back to non-negative integers, and let's add a single element to this semigroup, which will be denoted as infinity. So we extend the usual semigroup operation defined on non-negative integers to S by the following simple rule. We let n plus infinity equal infinity for every n. This is clearly an abelian semigroup, and let's observe that the respective Grothendieck group is 0. Why is it so? Well, because if we have any group homomorphism, semigroup homomorphism from S to a group H, we simply apply F to this identity, and cancel f of infinity, and we deduce that f of n is 0. And so the Grothendieck group is 0. Okay, so let's now discuss a construction of the Grothendieck group. Actually, we'll discuss two constructions. The first one is absolutely straightforward. And the second one is a little bit more involved, but is much more useful. Construction one involves taking a suitable quotient of a free abelian group. So let F denote the free abelian group with basis S. So it is just ZS, the direct sum of many copies of the integers. So S is a basis of F, so we have a natural inclusion, J of S into F. Of course, this is not a semigroup homomorphism, so we simply make it into semigroup homomorphism by considering a suitable quotient of F. So let F0 be the subgroup of F generated by all elements of the following form: J of X plus J of Y minus J of X plus Y over all X and Y in S. We now let G denote the quotient of F modulo F0, and we define a map I from S to G by composing J with the respective quotient map. And then it's a simple exercise to show that G together with I is indeed the Grothendieck group of S. So it satisfies our universal property. Let's now look at another construction of the Grothendieck group, which is much more concrete. Construction 2. Here we assume that S is non-empty. Let's consider the product of S by itself, and let's introduce an equivalence relation. We define an equivalence relation on S cross S as follows. We say that two pairs x1, y1 and x2, y2 are equivalent by definition if there are elements z1 and z2 in S such that the following two pairs are equal: x1 plus z1, y1 plus z1, and x2 plus z2, y2 plus z2. So roughly the idea behind this construction is to define the Grothendieck group to be a set of all formal differences. Of the form x minus I, where x and y run over S. So the formal definition of such a formal difference is as follows. We define an equivalence relation on the set of all pairs, and we consider the quotient of S cross S modulo this equivalence relation. So we let G denote S cross S modulo this equivalence relation. Well, a simple exercise is to show that this is indeed an equivalence relation. Clearly it is reflexive and symmetric, and a short calculation shows that it is transitive, so it is an equivalence relation. And moreover, it can be also defined in a slightly different way. Namely, two pairs x1 and y1 and x2, y2 are equivalent if and only if there is an element z in S such that x1 minus y2 plus z equals x2 minus, plus of course, there is no minus here, x1 plus y2 plus z is equal to x2 plus y1 plus z. This form of our equivalence relation is useful because it already implies that if S is cancellative, in particular, if S is cancellative, which means that we can cancel in S if we have three elements A, B, and C, and A plus C equals B plus C, then necessarily A equals B. So such semigroups are called cancellative. In Russian there is no single word. Можно было бы сказать сокращабельное, но обычно говорят полугруппа с сокращением просто. So if S is cancellative, then two pairs x1, y1 and x2, y2 are equivalent if and only if x1 plus y2 equals x2 plus y1. So this is very close to our original idea of taking formal differences because this pair represents x1 minus y1. And of course x1 minus y1 is equal to x2 minus y2 in any group if and only if I have this property. Okay, so we get an equivalence relation, we can form the quotient, and we can define an operation. So if we have two pairs, x1, y1, and x2, y2, then we define an operation on G as follows. So we simply add them component-wise, x1 plus x2, y1 plus y2. And again, a straightforward exercise is to show that this operation is well defined. And it makes G into an abelian group. So more exactly, if it wants to be a group, so it must have a neutral element. The neutral element of G is the equivalence class of the following pair, x, x, for any x in S. So all such pairs are easily seen to be equivalent, and this is a neutral element of G. If I now take an arbitrary pair, then the inverse element minus this pair is the equivalence class of yx. Because if we add these two pairs, then we get x plus y, which is the neutral element. So we obtain a group, an abelian group. And to show that this is indeed the Grothendieck group of S, we must also just define this universal homomorphism I. Well, let's define I as follows. I from S to G. So it takes x to the equivalence class of x plus x and x. Again, this is quite reasonable because this pair represents what it represents x plus x minus s, that is x itself. And finally, it's easy to show that this is indeed the Grothendieck group of S. That is, we have the respective universal property. Okay, let's look at some simple properties of the Grothendieck group. Properties of GR of S. First of all, it is generated by S in the following strong sense. It is I of S minus I of S. And more exactly, every equivalence class of a pair xy is equal to I of x minus I of y. This is a simple calculation. In the case of a cancelative semigroup, it is absolutely immediate because of this characterization of our equivalence relation. In the general case, the proof is also absolutely straightforward, and this is a simple exercise for you. Property 2 is as follows. Let's look again at this canonical map I. So I claim that I is injective if and only if S is cancelative. So in this case, the Grothendieck group contains the original semigroup by means of I. If S is not cancelative, then I is not injective, which is quite natural because, well, any abelian group is obviously cancelative. Property 3 is that the Grothendieck group depends naturally on S. This is a functor from category of abelian semigroups. Let's denote it somehow like abelian semigroups to the category of abelian groups. Well, this is a functor. And just by the very definition, this functor is left adjoint to the inclusion of this category into this one. This functor is left adjoint to the inclusion of abelian groups into abelian semigroups. And finally, it's easy to show that it is additive in the sense that if we take two semigroups S1 and S2 and apply the Grothendieck group, then the resulting group will be isomorphic to the direct sum of the respective Grothendieck groups. Okay, now we are ready to define the functor K0 of a unital ring. We have the following definition. Suppose that R is a unital ring. We define K0 of R to be the Grothendieck group of the semigroup V of R of equivalence classes, of isomorphism classes of finitely generated projective R modules. Well, so we see that this is the composition of two covariant functors. So it is also a functor. K0 is a functor from unital rings to abelian groups. This is a functor. Since both V and the Grothendieck group are additive functors, they have this property. The same is true for K0. So we have the following nature of isomorphism. And also K0 doesn't change if we replace R by the opposite ring. This follows from the respective fact about V of R. K0 of the opposite ring is naturally isomorphic to K0 of R. Well, here is a simple example. If little k is a field, then K0 of k is isomorphic to the group of integers for the simple reason that V of k is the semigroup from negative integers, and taking the Grothendieck group, we get the group of all integers. And for the same, more or less for the same reason, if R is any principal ideal domain, then K0 of R is isomorphic to the integers. Well, we'll construct more interesting examples fairly soon. Let's now look once again at the structure of K0 of R. So let's introduce some notation. If P is a finitely generated projective R module, then the respective element of K0 will be denoted like this. There is a slight abuse of notation here because we have used the same notation to denote the respective element of V of R, and this is not the same. But we are not very much interested in V of R. We are interested in K0 of R. So I hope this abuse of notation will not lead to any problems. Our description of the Grothendieck group readily leads to the following simple result. So K0 of R consists of all elements of the form of all differences of the respective elements corresponding to finitely generated projective modules, P and Q. And this description can be also simplified as follows. We can consider all difference of the form P minus Rn, where P is a finitely generated projective module, and N is a non-negative integer. So we can replace one of these two modules by a free module, and this gives the same group K0 of R. If we now have two finitely generated projective modules, P and Q, then the respective elements of K0 of R are the same, if and only if there is another finitely generated projective module L such that P plus L is isomorphic to Q plus L. And again, we can replace here L by a suitable free module, and we get equivalent property. There is a non-negative integer n such that P plus Rn is isomorphic to Q plus Rn. And there is a special name for this property. Such modules are called stably isomorphic. P and Q are stably isomorphic. If they satisfy condition 2. proof is almost immediate from our description of the Grothendieck group, or more exactly from this formula. The only question is why can we replace Q by Rn? But this is immediate from the fact that every projective module is a direct summand of a free module. So for every Q, we can find another finally generated projective module Q prime, such that Q plus Q prime is isomorphic to Rn for a suitable n. And so we see that the element P minus Q can be replaced by the following one, P plus Q prime minus Rn. And this proves part 1. And the same argument works in part 2. If P plus L is isomorphic to Q plus L, so first of all, we observe that these two properties are indeed equivalent by well, I have not stated this exactly, but maybe it would be good to state it here. So let's observe. This will be 1 and 1/2. So in the general case, I of x equals I of y, if and only if there is an element z in S such that x plus z equals y plus z. Again, this easily follows from our construction of the Grothendieck group. So property 2 is just a special case of this one. So if we now apply this to modules, we see that this condition and this condition are indeed equivalent. And to show that these conditions are equivalent, condition 2 and condition 3 are equivalent, we find a module L prime such that L plus L prime is free. And find L prime such that L plus L prime is isomorphic to a free module. And this reason implies that P plus Rn, we simply add L prime to both sides of this formula, and we deduce that P plus Rn is isomorphic to Q plus Rn. And that's it. Well, one final remark, which explains, actually this is a simple exercise, which explains why we consider only finitely generated R modules. So an exercise is the following. We take any unital ring R, and we consider the following semigroup, which is denoted by V infinity of R. This is the semigroup of equivalence classes of countably generated projective R modules. So in other words, we apply the same construction, but not to finitely generated, but to countably generated projective modules. It turns out that in this case, the respective Grothendieck group is 0. So it gives us nothing interesting. So this explains why we restrict to finitely generated projective modules. Okay, so that's all for today. At the next lecture, we discuss another description of K0, which is especially useful in the functional analytic setting. So we may describe elements of K0 of R as equivalence classes of idempotents in matrix algebras over R. Then we define, when we extend our definition of K0 to non-unital rings, which is also unavoidable in the C-star setting. So many natural C-star algebras are not unital. And then we prove a useful half-exactness property of K0. Okay,